Okay, welcome to these NPTEL lectures on basics and advanced concepts. In this week, we'll look at motion planning and linear control of robotic manipulators. So there'll be 3 lectures this week. The first lecture will be on motion planning. The second lecture will be on control of a single link using linear control. The third lecture will be control of multi-link serial manipulators, again using linear control. So first lecture is on motion planning. Let's start. So what do we mean by motion planning? We need to specify the trajectory of a robot manipulator. And what do we mean by specify the trajectory of a robot manipulator? Basically, we need to specify the time history of position, velocity, and acceleration of actuated joints or the end effector. Okay, so it could be either in terms of the theta, which is the joint variable, or it could be in terms of the end effector position and orientation. So what do we need? We need to develop algorithms for planning and generation of this trajectory. The main issues in motion planning are that there should be ease and flexibility in planning. Okay, it should also be that the trajectories which are being planned are sufficiently smooth so as not to cause vibration or jerky motion. Okay, vibration or jerky motion in a robot manipulator will decrease the life of the manipulator. We should also efficiently represent the trajectory in a computer and generate this desired trajectory in real time when required. Okay, so we will look at what is meant by real time little later. Okay, so there are 2 main ways a robot trajectory is specified. The first is joint space schemes. So basically it means the time history of a single or multiple joints as a function. Okay. In Cartesian space schemes, the time history of position and or orientation of the end effector is specified. And what is typically specified? The initial and final points in joint space or Cartesian space is specified. Often the initial and final desired velocity is also specified. Additionally, sometimes via or intermediate points are specified, and these come in 2 varieties, sometimes with the desired velocity at the via points or without the desired velocity at the via point. Most robots require at least that the second derivative or acceleration is continuous between the initial and final points. Okay, so this is known as C2 continuity. The trajectory update rates are typically between 50 and 200 Hertz, so between 20 and 5 milliseconds. So every 20 milliseconds or every 5 milliseconds, we need to generate either the position of the joint theta, theta dot, theta double dot, or the position and orientation of the end effector and its derivatives. Okay, so this representation and computation of trajectories must be efficiently done. So it is not a very serious issue with modern processors. Modern processors can easily generate the desired trajectories in 5 milliseconds or even faster. So let's continue. In joint space schemes, basically the plan of the trajectory of, let's say, theta 1. What is given? Theta 1 at T0 to theta 1 at TF are given. Okay, so where T0 and TF are initial and final time. There are infinite number of smooth curves which can connect theta I T0 to theta I TF. Okay, this topic is called interpolation. Okay, which is nothing but choosing a smooth curve between 2 given points. This is very well studied in CAD and geometric modeling. In robotics, we will look at the simplest possible manipulators. And what is the simplest possible polynomial? It is a linear polynomial between 2 given points. So theta 1t can be represented in terms of theta 1 tf minus theta 1 t0 divided by tf minus t0 into t minus tf plus theta 1 tf. So this is this quantity is like the slope of the straight line connecting theta 1 tf and theta 1 t0. Okay, this is not very smooth, as we will see in the next slide. So in this picture, we are showing theta 1 along the y-axis and time, which is along the x-axis. So let's say the joint initially is at theta 1 t0. It will go to theta 1 ta, then it comes to theta 1 tb, then theta 1 tc. So at 3 time instants, ta, tb, tc, these are the intermediate theta which are given. Okay, and we end up at the final time. So if you do linear interpolation, or if you connect theta 1 t0 to theta 1 ta by a straight line, and likewise from ta to tb also by a straight line. So if each of these are piecewise linear segments, okay, through these 3 via points, then the derivative of this straight line is a constant value. So theta 1 dot between t0 and ta will be some value. Now when the straight line changes direction, the velocity will become from positive to negative. Likewise, again it changes direction, again the velocity will go from negative to positive. And if it changes slope again, then it will have a different positive value. So basically there are sign changes in theta 1 dot between segments, okay, and there are distinct changes in the value of theta 1 dot, even if there is no sign change. The plot of theta 1 double dot is even worse. Why? Because the derivative of this so-called step function, so when it is constant, it is 0. And then if it changes sign, there is a change in, so it's like a delta function which is happening at ta, tb, and tc. Okay, so it is not even C1 continuity. Okay, to obtain a simplest polynomial trajectory with C2 continuity, we can look at a cubic trajectory. So a cubic trajectory is given by theta 1 t, which is a0 plus a1 t plus a2 t squared plus a3 t cube, where t lies between t0 and tf. And this a0, a1, a2 and a3 are 4 constant coefficients which needs to be determined. So to obtain these 4 constant coefficients, we use the fact that theta 1 is given at t0 and tf. Similarly, theta 1 dot is given at t0 and tf. So theta 1 t0 is theta 1 0, theta 1 tf is theta 1 f, theta 1 dot t0 is theta 1 dot 0, and theta 1 dot tf is theta 1 dot f. Okay, so if you substitute these 4 given position and velocities at t0 and tf back into this equation, cubic equation, we will get 4 linear equations in 4 unknowns. Okay, a0, a1, a2 and a3. So for the sake of simplicity, let's assume that t0 is given as 0. So we start at 0 time. Then if you substitute t equals 0 in this equation, we will see that theta 1 0 is a0. Likewise, a1 will be theta 1 dot 0, and a2 and a3 will be in terms of tf and theta 1 f and theta 1 0 and so on. Okay, little complicated expressions for a2 and a3, but not very complicated. Okay, so as you can see, a2 is divided, one term is divided by tf square. In a3, one term is divided by tf cube. Okay, so as an example, let's consider that theta 1 at t equals 0 is 30 degrees, theta 1 at t equals 3 seconds is 60 degrees, theta 1 dot initially is 10 degrees per second, and theta 1 dot at t equals 3 is minus 30 degrees per second. So we substitute these 4 given quantities in the cubic equation, and we can show or derive that a0 will be 30, a1 will be 10, a2 is 13.34 and a3 is minus 4.45. So the units are dropped. So the expression for theta 1t is nothing but 30 plus 10t plus 13.34 t square minus 4.45 t cube. Okay, which we can plot. So this is a plot of theta1 as a function of time between 0 and 3. Okay, so this is the cubic curve which we have obtained. The derivative of the cubic curve is a quadratic. Okay, so this is the quadratic curve which shows theta1 dot as a function of time. And the second derivative of that cubic curve is a constant value. Okay, so that is the acceleration. So what you can see is theta1 t, theta1 dot t and theta1 double dot t are all continuous between t equals 0 and t equals 3 seconds. Okay, let's continue. You can see that this A2 and A3 requires division by TF square and TF cube. So for example, if TF is very large, let's say it is 5 minutes, and you are going to generate delta T at, let's say, 10 milliseconds, okay, or 20 milliseconds. So then this TF can become very, very large, and TF square and TF cube can also become very large. So the scale T as in geometric modeling, that is the solution to this problem. And this is given in some geometric modeling book by Mortensen. So we define a new variable u, which is T by Tf, and u will always lie between 0 and 1. And the derivatives of this cubic is denoted by T, but with respect to u, we denote it by a prime. So the cubic now becomes theta1 u, which is a0 plus a1 u plus a2 u square plus a3 u cube. Okay, if you substitute back all those given quantities, which is at t0, it is theta1 0, and derivative at t equals 0 is theta1 prime 0, and so on, we can show that a0 is given by theta1 0, a1 is theta1 prime 0, a2 is given by minus 3 theta1 0 plus 3 theta1 1 minus 2 theta1 prime 0 and minus theta1 prime 1. So 1 means at u equals 1. And likewise you can find a3. Okay, so basically resubstituting back a0, a1, a2 and a3 in this cubic, we can show that theta1 u is given by theta1 0 into 2u cube minus 3u square plus 1, then plus minus 2u cube plus 3u square into theta1 1, and u cube minus 2u square plus u into theta1 prime 0, and u cube minus u square divided by theta1 1. So basically, as you can see, there is no division by a large number. Okay, so we can obtain theta1 as a function of u, which lies between 0 and 1, and u is given by t by tf. Okay, but eventually we need to supply theta1 at every time instant. So we can convert back theta1 u back to t by using u equals t by tf. Okay, so we are not dividing by tf square or tf cube. This cubic, which is given here, okay, a0 plus a1 u plus a2 u square plus a3 u cube, where a's are given by these expressions, can also be written in a nested form, which is a0 plus u into a1 plus u into a2 plus a3u. Okay, so this is the nice compact way. What is the advantage of doing this? You can see that it requires only 3 multiplication and 3 additions. So when it was in this cubic form, it required 1 multiplication here, 3 multiplications here, and some u cube is 3 into a3. So 4 additions and several multiplications. Okay, in this nested form, we need only 3 multiplications and 3 additions to obtain theta1 u. We can also find theta1 prime u and theta1 double prime u by just doing 3 additional multiplication and 3 additions. Okay. So for an n-jointed robot, we generate this theta1, theta2, theta3, theta n separately. So basically we have n into 3 multiplications and 3 n additions to obtain the thetas of each one of the joints. So in a way, this cubic joint space scheme is very efficient. Okay, let us continue. One thing that you can see is the cubic can satisfy at most 4 constraints. Okay, so there are 4 parameters, A0, A1, A2 and A3. So there is no control over initial and final acceleration. We can only specify initial and final position and initial and final velocities. If you also want to specify initial and final positions, we have to use a 5th degree polynomial, which is also sometimes called as a quintic polynomial. So it is not very complicated, but we need a little bit more number of computations. Okay. So why do we need to specify acceleration? Sometimes in control, we will need both position, velocity and acceleration. It helps to specify or find out what is the desired velocity and desired acceleration also. Now let's continue. If you want to generate a cubic trajectory with via points, okay, let's say there are k via points specified, and as I had mentioned earlier, there are 2 possible cases. One is the velocity at the k via points are specified, and the other case the velocity at the k via points are not specified. Not specified means we don't care. Okay, so in the case of case 1, when the velocities are specified, so basically we have k plus 1 segment and we plan k plus 1 cubic. So between first initial point and the first via point, we plan a cubic. Between the first via point and the second via point, we plan another cubic, and so on. So for 2 points and k via points, we will have k plus 1 segments. So we just plan k plus 1 cubics. So for each one of those, we solve for A0i, A1i, A2i and A3i. Okay, all by using the same cubic equation. So in this case, we will see later that C1 continuity is ensured, but since we have no control over the acceleration, it is not C2 continuity. So there is a discontinuity in joint acceleration across the via point. Okay, example. So we have theta 1 at t equals 0 given us 30 degrees, theta 1 at t equals 3 given us 60 degrees, theta 1 dot as 10 degrees per second, and theta 1 dot at t equals 3 as minus 30 degrees per second. However, it is also specified that at time t equals 2, so in between 0 and 3, the angle should be 55 degrees and the velocity should be minus 10 degrees per second. So everything is specified. So there are 2 segments. For segment 1, A01 is 30, A11 is 10, A21 is 13.75 and A31 is minus 6.25. For segment 2, A02 is 55, okay, A12 is minus 10, A22 is 65 and A32 is minus 50. We just solve those 2 cubics with these boundary conditions at t equals 0 and t equals 2 and then t equals 2 and t equals 3. Okay, so the equations for the cubics are theta 1t from these coefficients 30 plus 10t plus 13.75t square minus 6.25 t cube, where t lies between 0 and 2. And likewise for the second segment, theta 1t is 55 minus 10t plus 65t square minus 50t cube, where t lies between 2 and 3. So we can plot this, and you can see that theta 1 as a function of time consists of 1 cubic up to 2 and another cubic from 2 to 3. The velocity, when you take the derivatives, you will have one quadratic here and another quadratic here. So you can see that there is a kink sort of thing which is happening. And if you take the second derivative, you will have a constant acceleration from 0 to 2 and a different constant acceleration from 2 to 3. So there is a jump. So the acceleration is discontinuous. In case 2, if the k via points are specified, but the velocities at the k via points are not specified, then we are free to choose to match velocities and accelerations at the via points. Okay, so let's start. So we have 2 cubics from 0 to tfi, I equals 1 through 2, 1 and 2. So theta 1t can be again represented as a0i plus a1t plus a2t square plus a3t cube, I equals 1 and 2. So from initial, final, via point and initial, final velocities, so there are 5 of these. Okay. We can substitute and we can show that theta 1 0 is a01, theta 1 dot 0 is a11, theta 1 v also we can get, but for the second segment theta 1 v also we can get as a02. Okay, so at the via point, the theta 1 at the end of the first segment must be equal to theta 1 at the beginning of the next segment. So we have actually now 6 constraints. So we substitute these 6 constraints in these expressions and we can solve, we can get 6 equations. Now what we can do is we can match the velocities and acceleration at the via point. Okay, so the velocity is the first derivative of this at t equals tfi will be equal to the start of the next segment. So we will get one equation which is a12 is given by a11, 2a21 tf1 plus 3a31 tf1 square. Likewise, we take the second derivative which is a22, 2a22 will be equal to 2a21 plus 6a31 tf1. So acceleration in the end of the first segment should be equal to the acceleration at the beginning of the second segment. So now you can see that there are 8 equations in 8 unknowns which we can solve and obtain all the 8 coefficients of the 2 parts of the cubic. So if you plot this for the same data, so you can see that the first segment A01 is 30, A11 is 10, A21 is minus 1.04, A31 is 1.15. Likewise for segment 2, A02 is 55, A12 is 19.58, A22 is 5.83 and A32 is minus 20.42. So this is 1 cubic till 2, this is another cubic from 2 to 3. If you take the derivative, this is a quadratic up till here and another quadratic up till here. However, there is no kink. Why? Because we have matched the velocities at the via point t equals 2. Likewise, the slope, since there is no kink, there is no jump in slope. So we have acceleration which is continuous, which is a straight line from 0 to 2 and another straight line between 2 and 3, but there is no discontinuity at t equals 2. Okay, so clearly as expected, theta 1 dot and theta 1 double dot are continuous. Okay, so for k via points, we can get 4 plus 4k equations, and it turns out this is the sparse matrix and we can easily solve for all the coefficients if you have k via points, but at the via points we match velocity and accelerations. Okay, so the joint space schemes is useful if a joint or a group of joints are to be moved. Typically we are looking at the motion of the end effector. Okay, so if you want to do motion planning in terms of position and orientation of the end effector, then we need to use what are called Cartesian space schemes for motion planning. Okay, so this is more natural for the robot operator to specify. The robot operator can say the end effector is moving along a straight line or it is moving along a curve in 3D space. Okay, it is easier to see and visualize and check for obstacles also. So if I say that I want to go from one point in the Cartesian space to another point in the Cartesian space, and if I generate the straight line, we can see if this in this straight line it is hitting any object or not. Okay, it is difficult to little bit to plan orientation due to the representations of orientation. Okay, remember orientation can be represented using rotation matrices, angle axis, okay, Euler angles and so on. So in all cases there are some small problems. Rotation matrix, lots of constraints. Euler angles, there are singular configurations. So Traditionally, two important Cartesian space paths are used for position planning. Okay, so one is called linear interpolation, which is basically nothing but straight line path between two given positions. The second thing is called circular interpolation, which is we go on a circular arc between three given positions. Okay, and as in any motion planning scheme, all paths must be C2 continuous in time t. So straight line motion, how do we plan a straight line motion for the end effector? So what are we given? We are given x0, y0, z0 at t equals 0, initial point, initial velocity x dot, y dot, z dot, final point xf, yf, zf, and final velocity x dot, y dot, z dot. Okay, so the equation of a straight line in 3D space can be represented by two equations. So it is like y equals mx plus c and z equals m2x plus c2. Okay, in general we can write as y is some slope into xt minus xf plus yf, and zt, z as a function of time, is some slope into xt minus xf plus zf. So we plan a smooth cubic trajectory for xt, as xt is x a0 plus a1t plus a2t square plus a3t cube. We compute the coefficients from the given initial and final conditions. A0 will be x0, a1 is x dot, and so on. So once we have x of t as a smooth trajectory, we can compute y of t and z of t from this equation. Okay, so which will ensure that all the generated xt, yt, zt are all C2 continuous, right? X of t is continuous, C2 continuous, so both zt and yt will be C2 continuous. And more importantly, all the xt, yt, zt are exactly lying on a straight line in 3D space. Okay. Sometimes for smoothness, we specify circular arcs as opposed to piecewise straight lines between 3 points. So if you are given 3 points, I can do two straight lines, or I can pass a circular arc. So circular arc is a little better preferred, because it is more smoother. Okay, in terms of 3D space, in time we will always be smooth. So how do we obtain the trajectory when three given points, let's say P1, P2, P3, all in some fixed coordinate system are given, and the velocities at these points are also given? So first thing is we need to define an algorithm for circular interpolation, meaning what? We find out the equation of the circle. All these 3 points will lie in a plane, so we need to find the equation of the circular arc in this plane. So what are the steps? First thing is we compute the normal to this plane. So there is a vector from P1 to P2, another vector from P1 to P3. The normal to this plane is the cross product of these two vectors. We also need to make sure that they are unit vectors. Then we compute the location of the axis in this plane. Let's call them x, y, and z. So the z axis is along the normal. The x axis is between P1 and P2, again made into a unit vector, and y axis is 0 and cross x, so right-handed coordinate system again. So these x, y, and z axis will define the coordinate system CIRC, from denoting circular. Okay, so what is the rotation matrix of this coordinate system CIRC with respect to 0? The first column is the x-axis, which is this. Second column is the y-axis, which is this, and third column is the z-axis, which is the normal to the plane. So now we transform this 0p1, 0p2, 0p3 to this coordinate system CIRC using a transformation matrix CIRC0R. So you can see CIRC0R into 0p1 will give me this point p1 in the CIRC coordinate frame. Okay, So in this CIRC coordinate frame, the points will be xi, yi and ci. So the z coordinates will not change, okay, because all three are in a plane. So now from these points xi, yi, ci, we can compute a and b, which is the center of the circular arc, and r, which is the radius of the circular arc. Okay, how can we do it? There are many ways. So one is you connect xi, yi, x1, y1, x2, y2, x3, y3. You draw the straight lines, find the common perpendicular bisector of these two segments. Wherever they meet, that is the center of the circular arc. And then radius is from the center to any one of the points. We can also compute the angle made by the line from the center to the 3 points with the x-axis in CIRC. So let's denote them by phi1, phi2 and phi3. Okay, so I found the center, I found an x-axis, and then from 1, 2 and 3 I can find the angle. Okay, we can plan a C2 cubic trajectory for phi of t such that phi1, phi2, phi3 are reached in the specified order and in specified time t. Okay, so maybe at t equals 0, then t equals some tf1, and then some t equals tf2. Okay, so once we find this circular arc, the equation of a points on the circular arc will be given by x of t, which is a plus r cos phi t, and y t, which is b plus r sin phi t, and zt will be constant. Okay, so since phi of t is C2 continuous, it is done using a cubic trajectory. Xt, yt and zt are also C2. Okay, and then finally, to obtain the end effector path in the zeroth coordinate system, the fixed reference coordinate system, we pre-multiply x, y, z by the 0 CIRCR. Okay, so what have we done? Basically, we have taken these 3 points, find the equation of the center of the circular arc in some plane, then planned a trajectory in that plane, and then converted it back to the zeroth coordinate system. The alternate would be to use inverse kinematics and plan the trajectory in joint space. So if I give you x, y, z, we can do inverse kinematics, find theta 1, find the joint angles, plan the trajectory in joint space, and then convert it back to the x, y, z. However, this will only give you approximate straight line, okay, or circular trajectory in Cartesian space, because only at the points where you do the inverse kinematics it will be exact. In between it will not be exact. Trajectory planning for orientation. So as I said, there are various representations of orientation, all with their own advantages and disadvantages. Okay, when you want to do trajectory planning for orientation, it turns out that this representation using Euler parameters is most suitable. So Euler parameters are nothing but 4 parameters plus 1 constraint. So we have some 0, epsilon 1, epsilon 2, epsilon 3 in the zeroth coordinate system, and a scalar epsilon 4. So what are we given? We are given this vector at t equals 0, epsilon 4 also at t equals 0, and likewise this vector at tf and epsilon 4 at tf. So we have to ensure that the square epsilon 1 square plus epsilon 2 square plus epsilon 3 square plus epsilon 4 square is always 1. Okay, and this interpolation must satisfy this constraint at all time t. So what do we do? What is given? We are given some initial and final Euler parameters. We are also given initial and final angular velocity of the end effector. Okay, remember in position we are given initial and final position, but also the initial and final velocity. In the case of rotation or orientation, we can only specify angular velocity. Okay, and if you go back and remember, the angular velocity is not directly related to the rotation matrix. Okay, or it's very simply related to the rotation matrix. It was some r dot r transpose and so on. So we need to find the relationship between angular velocity and Euler parameters. This is not as simple as xt and x dot t. But it turns out that there is a relationship, which is why Euler parameters are used. So it turns out that the angular velocity of the tool coordinate system can be written in terms of rate of change of the Euler parameters epsilon dot and epsilon 4 dot pre-multiplied by a matrix 2et. Okay, E is given here below. The inverse is always also possible. So if I gave you the angular velocity of the tool, I can pre-multiply it by half ET transpose and get the rate of change of epsilon dot 1 dot, epsilon 2 dot, epsilon 3 dot, and epsilon 4 dot. And E is a non-square matrix. So this is the interesting part. So I am going from omega to epsilon or from omega to epsilon, both directions, but I am not inverting any matrices. Okay, so it turns out that this is the real nice feature of Euler parameters. So for a given E of t, which is specified by minus E1, E4, minus E3, E2, this is a non-square matrix. This, in one case we use 2et and one case we use half et transpose. Okay, so what can we do to plan trajectory for orientation? Okay, we plan C2 continuous trajectories for given Euler parameter at t equal to 0 and rate of change of Euler parameters at t equals to tf. Okay, we compute the trajectory for epsilon 4. So epsilon 4 is not generated. Epsilon 4t is given by plus minus 1 minus epsilon square. So this ensures that the constraint is always satisfied at all t. Okay, so from epsilon of t and epsilon 4 of t, obtain any required representation of the orientation of the end effector at each instant of time. So if I want to show you what are the Euler angles, I can obtain from epsilon 1, 2, 3 and 4 what are the Euler angles. I can also obtain the rotation matrix or even the axis and angle. So in summary, the joint space schemes can be applied for all actuated joints in a robot independently. Okay, so when I'm planning the trajectories for theta 1, I don't need to worry about what is happening to theta 2. In parallel manipulators with passive joints, interpolated actuated joint values must satisfy the constraint equation containing passive and actuated joints. Okay, this is important to see or to check. Okay, straight line or circular trajectories may pass through singularities or points not in the workspace. Okay, so I have tried to move from one place to another place. In between there is a hole in the workspace. So even though the initial and final points are in the workspace or far away from singularity, in between points can be outside the workspace or close to a singularity. So these needs to be checked also. Okay. Straight line and circular trajectories must be checked for singularities, whether it lies always in the workspace, and also for joint limits. This is important. Okay, so not all joints in a robot can rotate fully. Till now we are assuming theta, there are no constraints on the joint limits, but if there are joint limits, we need to check for that. Finally, all these end effector trajectories or even the joint space trajectories that we have generated do not take into account the dynamics and torque limits of the joint. Okay, so we can peacefully go and plan a trajectory. However, it turns out that in some place the desired acceleration is very high, okay, and it cannot be supplied by the motor which is there in the robot. So if you want to plan trajectories taking into account the dynamics or the torque limits, then we need to do more advanced joint motion planning. Okay, this was done in a paper by Bobro in 1983, long time back. So it is not a very new thing. So with this we come to this end of this lecture on motion planning. In the next lecture we'll look at control of a single link.